All right, we're entering into the final stretch in this course, and it is on quantum theory. So we're in Unit 5, Modern Physics. We've looked at the special theory of relativity. The second part of this unit looks at quantum theory and quantum mechanics. So first we're going to introduce the concept of quantum theory. This starts on section 12.1 in your textbook. So in classical physics, we had Newton's laws that describe forces, and Maxwell's work on electromagnetic radiation formed the basis of the study of mechanics, electricity, and magnetism. So that's basically, we had that understanding that physics was kind of, the thought was we're close to solving everything. We know how electricity and magnetism are related. We know how electromagnetic radiation propagates. We know how things work in terms of forces using Newton's laws. We had a few questions about some things such as how light can emit electrons and a few other kind of questionable things about travel near the speed of light. And it was the early 1900s when some new thoughts were brought into the realm of physics, and they kind of broke the whole thing apart. So one of the things, when we looked at very, very small, the very, very microscopic world, the subatomic world, there were some very strange things that were happening. So the laws of physics weren't working exactly there. And on this slide, it says physicists such as J.J. Thomson discovered that Newton's laws failed to explain the behavior of electrons and atoms. Similarly, although Maxwell correctly described electromagnetic phenomena in the everyday world, his equations failed in the microscopic world, the quantum world. So the smaller we go, the more these laws would break apart and they wouldn't hold anymore. So we needed to come up with some laws to understand the quantum world. But there really should be universal laws. So there was this overarching idea that maybe we fully don't understand everything that's happening in our world. So a quantum, it refers to a very small parcel of energy. So quantum kind of refers to quantity, which means countable. So it's a countable amount of energy, a small countable amount of energy. So if you can think of it like, let's assume that energy is only delivered in small packets, and the size of each packet was, say, a 1 centimeter in radius sphere. Well, we can count how much energy we have if we can count each of those little spheres. This is the same idea with the electron, and with the electron, when we were talking about the fundamental charge of an electron, that smallest possible charge that exists, which is equal to 1.6 times 10 to the negative 19 coulombs, that was discovered by Millikan. So that was the smallest possible charge. We can count charge as a whole value multiple of a number of electrons. So quantum's the same idea, but it relates to energy. So I'd like you to copy down the definition of quantum, and quantum theory, which is also on this page. That's the theoretical basis of modern physics that explains the nature and behavior of matter and energy at the atomic and subatomic levels. So, next slide here says, according to Newton's laws and Maxwell's equations, energy can be carried from one point to another in two ways. So we have by particles and by waves. So if we're talking about particles, we can think of, say, something that has a solid mass to it, like a tennis ball, and waves are a transfer of energy. So we understand how particles and waves kind of move through our universe, but in the quantum world, our understanding kind of breaks down. So it says here for the note, which I'd like you to copy down, many models in classical physics break down when applied to extremely small objects such as electrons. Now, we're going to go back to the double slit experiment, and you might have seen this if you were kind of searching online for the double slit experiment, because a lot of what you'll find actually refers to the double slit experiment with electrons. Originally, of course, we know that Young used the double slit experiment to see how light, or to prove that light is a wave by showing that light interferes. But I have a short video to show you, and then we'll come back to this. And that will explain to us how the double slit experiment kind of works with particles. So I'll show you that video now, and then we'll come back to this slide.
So, what they taught us in school isn't really the way it is, and that our senses are playing tricks on us. You just gotta wonder, what is this reality that we find ourselves in? Quantum physics says it's all just waves of information. Do I believe that? I hope so. Yikes! And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange, never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So what we saw in that video was that matter, electrons, can behave like waves. So just to go through it again, I'll read through these slides, and then I'll make some extra comments as well. So it says here, when light passes through a double slit, we have the constructive and destructive interference that produces the bright and dark fringes on the screen. This is similar for sound waves and water waves. So we're already familiar with that from Unit 4. But classical objects, so particles like tennis balls, if we shot them at a double slit, we would expect that they would hit the screen in a pattern that basically looks like two bars that are at the end of the screen that are directly related to the location of where the slits are. However, so I guess before we get into that, let's copy this down. I want you to copy this here. Particles, they do not show interference effects. They deliver their energy in discrete quantities. Waves show interference effects, and they deliver their energy continuously over time and are spread out over the screen. So that table I want you to copy. You might want to pause to do that. Now, in the quantum world, and electrons are an example of a quantum particle because they are subatomic. So as we shoot electrons, I know in the video they did show that when you shoot electrons at a single slit, there is no interference shown. They just hit the wall at the bar at the opposite end of where the slit is. But when we have the double slit and we shoot electrons at that, we have basically an interference pattern that shows up where they would hit at a number of different locations. And this is explained on page 617. Figure 2 explains this. So this shows what you would see in a double slit experiment if you shot a finite number of electrons through the screen. So case 1 has 20 electrons, and then case 2, 3, and 4 we start to increase the number of electrons. So that's what this picture is showing. Actually, sorry, it's there if you haven't seen it. When we have more than 10,000 electrons, we start to see the more distinct interference pattern. This is an example of what you would see that interference pattern. So each time an electron hits that screen, the screen would, which was dark, would lighten up a bit. So you can see the bright spots where the electrons hit more frequently, and the darker spots where the electrons hit less frequently. That's what our screen would look like. So again, in this case, the electrons produce the same pattern as light in a double slit experiment. Now, why was this such a big deal? Well, it shows that electrons can exhibit interference, which is something that in the classical theory we knew was only possible for waves. And it shows some aspects of particle-like behavior, because the electrons, they arrive one point at a time on the screen. So instead of delivering their energy continuously, they still deliver their energy in parcels. So this wave-like behavior is characteristic of the quantum world. Electrons, protons, atoms, and molecules all give the results shown. So if we were doing this with electrons, but if you did this with protons, which are also subatomic, or atoms, and molecules, which are atomic, you would see the same results. Conversely, light and other electromagnetic radiation can exhibit particle-like behavior. So the clear-cut distinction between particles and waves breaks down in the quantum world. So what we refer to in, how we refer to this in physics is the wave-particle duality. So when we're talking about quantum objects, they exhibit wave-like and particle-like behaviors. So all quantum objects, including EM radiation and electrons, can exhibit interference, and all quantum objects, including EM radiation and electrons, transfer energy in distinct or discrete amounts. So those amounts, those parcels of energy, are called quanta. So when we're dealing with quantum mechanics and quantum theory, waves and matter are able to exhibit interference, and they're also able to deliver their energy in parcels, finite quantities. So write down this, these terms for classical physics. Classical physics is, of course, the physics of things like Newtonian mechanics and Maxwell's theory. We can use all that. And only waves exhibit interference. Only particles deliver energy in discrete amounts. This is our classical physics understanding. And then quantum physics, the quantum world, this is where we're talking about subatomic, which are things that are smaller than an atom, and atomic, which are things that are of the same size as an atom. And the wave-particle duality is a property of matter that shows that when we're talking about the quantum world, matter has both wave-like and particle-like characteristics. So please copy this slide down as well. So here, I won't do this, but basically it says if you hit 50 golf balls at a barrier with two narrow slits, what would it look like? Well, you'd have two bars directly across where the slits are. And they would be, sorry, I shouldn't say bars, but you'd have two areas of small little circles where the balls hit, because they're delivering their energy in quanta, in parcels. So if we used electrons instead, because electrons are quantum particles, they would interfere with each other. So you would see that interference pattern that you would normally see with light going through a double slit. So the idea that electrons and all forms of matter have wave-like properties was one of the concepts that shook the world of physics in the early 1900s. This discovery, along with the observation that light behaves like particles, helped form the basis of quantum theory. So this seems pretty out there in terms of quantum theory. and it doesn't seem like there's many practical applications. And at the time, when this was being proposed, there was a lot of confusion on what could possibly be the applications of quantum theory. Well, what we found is that while there wasn't an understanding of how we can use this new understanding at the time, once the physics of quantum mechanics was starting to be defined, scientists and engineers started to apply that physics to create new products, new inventions. Electron microscopes, lasers, semiconductor electronics, these were all practical applications of a theory that was thought to be useless in the I guess the engineering sense. So this kind of goes to show the how the science technology cycle works. Science ends up finding new discoveries. The engineers and the technologists end up using these discoveries to create new technology. That technology creates new problems, and scientists end up finding new solutions or coming up with new understandings, which then go back through the technology cycle to come up with new solutions. So now this unit, you might notice it's kind of it's actually pretty heavy in terms of I guess knowledge and understanding. So there's going to be a lot of explain type questions you'll see, not as much math, because the math is actually pretty much above the level of this course, with the exception of a few things. So if you're having any difficulty understanding, feel free to ask me questions on our course website, because I want to make sure that everybody has a full and strong understanding of this. I know it's very new and novel and difficult to understand at first, but if you're having trouble, please feel free to reach out to me, and I'd be willing to help.